Perfect. We're live. Let's wait for 2, 3 minutes, maybe up to 5 minutes for people to join and we can get started.
So I could start to share my screen now.
Yeah, that's a great idea. Okay, we already have 8 people watching on YouTube. Hi everyone, let us know where you're joining us from today. Are you in the United Kingdom? Are you in Asia? Are you somewhere else? 9 people, okay, more people joining. Hi everyone,
Hi
we will be
everyone.
starting in a few minutes. In the meantime, if you have chat on the platform you're joining from, feel free to let us know where you're joining from so we can, because it would be good to know more about our community. 11 people. Hi everyone, thanks for joining us. We will be starting in a few minutes. London, perfect. Yes, we're based in London as well. Han, you stopped sharing.
Oh,
Okay, perfect.
I'm back.
Okay, we have 15 people watching. More and more people are joining. That's great. Uh, so I guess we can start at 5 past 5. India. Oh, nice. We have people from many different places.
Can everybody see my share screen all right? The slides?
Yep. And I think we can get started.
Okay.
So yeah, Han, the floor is yours.
Okay. Hi. Good afternoon, good evening, and morning. So my name is Han Rui, and welcome to this seminar, Introduction to Quantum for Decision Makers. Currently, I'm the director and co-founder of a new company called BQt. We are a quantum tech and consulting firm focused on education and training for industry-related activities in quantum computing. And I have obtained my PhD in quantum computing back in 2013, so like quite a while ago. And since then, I have been really with the field all the way along, working in academia, government agencies, as well as in the industry. Um, And I don't know how much you know about quantum, but from the title, we are doing an introduction, right? But even for introduction, there's actually a lot to talk about for quantum technologies. So which I certainly cannot cover for this seminar, but um, let me, yeah. Okay, but I just wish that by the end of the seminar, I could actually briefly answer those 5 questions, which what I think are important for business decision makers. So the very first one is quantum technology. What is that actually? When we say quantum technology, what do we mean, right? And then the next, where does the power of quantum information or quantum computing coming from? Um, why are we interested in this? Why is that powerful than our current computer, right? And then what are the applications of quantum technologies of quantum computer? What is actually the state of art? How far are we from having a real like workable quantum computer? And where are we heading to next, right? Which may be the most important thing for decision makers to see when you want to get into the field and when you want to invest. Right, so let's start. The very first quantum technology that I'm going to talk about is probably the one that you hear already a while ago. It is called quantum communication or quantum security, right? And under this name, there are 2 strings: quantum key distribution and post-quantum cryptography. And then later, there's also quantum internet, like it's kind of internet in the same way, but for quantum information rather than classical information. So here, maybe you were saying that I would call a computer, not just a computer, but a classical computer or a quantum computer. So when I say classical information or classical computer, it's actually what we have been using our daily understanding of computer information. And when I talk about quantum, that's really specifically for things that comes with the quantum technology, just to make the terminology clear, right? And why do we care about quantum communication, right? So there is this RSA coding system, encryption system, which is the most well-known and widely used encryption systems that is backing on our secure data transformation on the internet with the call that we are doing now, or your bank transformation, or other privacy data protection. And that is based on a factorization algorithm. It has been safe for the last decades, which RSA would also be safe towards any eavesdropper attack with classical computers, right? However, in 1994, also more than 3 decades ago, Peter Shor find out the algorithm that would actually offer exponential speed up in factorization, right? If the factorization can be exponentially fast, then the RSA code would no longer be secure. Means that all the encryption, 90% of the encryption systems that we are using now would be cracked. But this requires a quantum computer. It requires a quantum computer with about 2 million qubits. I don't know, 2 million is actually, in the classical world, it's a very small number. Like your USB disks definitely have million times more bits than this 2 million, right? But for quantum computer, it's actually quite challenging, and we will come to why is that so later. And then because of the threat that we might get from quantum computer in the future, we need to do quantum safe communication, right? Although a quantum computer is not here with us yet, or a quantum computer that can actually implement a Shor algorithm is definitely not with us at the moment. However, there is something that really worries the community a lot that's called harvest now and decrypt later. What does it mean? It means that, okay, the data has a shelf time, right? So for some of the data, the shelf time could be just instantaneous, right? But for other things like your health information, your bank information, your financial situation, or a lot of other things that actually the shelving time are like 10 years or 20 years, which they will still be relevant. And then there is migration time. When we implement a new encryption systems, the migration is not easy. It usually takes years, right? And if this data shelf time plus the system migration time is longer than the quantum computer development time, so the day that we will actually get a useful quantum computer for the Shor algorithm, then we will be in big trouble. At this point, all the data that is securely stored in the past would no longer be secure at all. So if anybody gets a hands on the quantum computer of this power, then he or she would have all the data that are secure and maybe can fake bank transformation or doing a lot of harms. So the whole community is actually working towards implementing quantum safe communication right now. And there's two strategies. One is quantum key distribution, that is using a quantum system like photons that are entangled to communicate information, to give you a public key. And another one is post-quantum cryptography, which is actually a completely classical encryption system. It requires a lot more complexity than RSA. That's why they were not used now, but they are believed to be more robust towards attack from a quantum computer. So this is quantum communication, right? And then the next, which is actually the oldest quantum technologies that has been around us, is called quantum metrology or quantum sensing. As we actually can see from here, right? This is a MRI machine in the medical centers, and they are using quantum technologies without you knowing about it. So they actually use spins of molecules that can be detected. The spin can be detected with quantum detectors, the magnetic fields, and then get a very precise image of your body, which is much better than classical technologies like X-ray or CT. Yeah? And then we have atomic clock, which are also right now being actually influencing our daily life, because the word second is defined based on the transition of the atom cesium. So scientists are still working towards making the second more and more precise. And then there's quantum magnetometer and quantum gravimeter, which actually could look like this. So this is one of the models that I actually take from one of the companies doing quantum sensing. So they put a quantum systems there, and then they can detect things in a much more precise way than a classical detector. So for example, quantum gravimeter could allow us to do navigation without using a GPS system. Okay. And then last but not least is quantum computing, which we will actually focus for most of the time for this talk. The words that I'm going to just give you some of the important components here is quantum hardware and quantum simulation, quantum algorithms, and QEC is quantum error correction. Okay. Later, they will probably make more sense to you than it is now. But so those are the quantum technologies, right? What are we actually doing for the market? What is the overall landscape at the moment? So this is a graph from QERA for the global effort from the national strategies or national investment of 2025 towards quantum technologies. So the total number is about 56 billion US dollar. And if we look at who are the leading ones, right? China has 15.3 billion, which it's just estimate. We actually don't know how much they are actually investing in this, which could be much bigger. And then the United States is actually Japan comes second, which is about 5 billion, and then it comes US, UK, and Germany. So actually, UK is not a small player for quantum technologies, especially for quantum communication, actually. And then, how about the venture activities, right? So this is from a JP Morgan article, for which we can see that 2025 is the year that there's a huge boost in the venture activities towards quantum startups and companies. It's so this gives us about 4 to 5 billion US dollars. And I have to say that most of this investment, or more than half of them, actually are invested in 3 companies, which are Quantinuum, PsiQuantum, and IonQ, which IonQ is actually a publicly listed company in the US. And I believe Quantinuum is going to get IPO end of the year or beginning of next year. PsiQuantum is having its IPO in February. So if not yet, but some in the coming days, this month. Okay. So there's a lot of investment going into quantum, but compared to AI, which is actually one of the things that people talk about the most at the moment, right? The number is probably small, mostly because quantum technologies is not ready yet, right? So those are still investments into a very, I would not say a newborn, but maybe a kindergarten stage of a technology. However, AI is and now at the moment with us. So that's why somehow people in the field of quantum technologies could also sometimes say that we are actually in a quantum winter. But looking at these figures, I'm sure that we are actually not in a winter. It's constantly growing. It's good that sometimes it helps down a little bit so that people can focus on the more important things. But I think we're still going on the right track. So yeah, who are the companies that are doing quantum technologies, right? So this is actually a very incomplete chart that I think this was updated in 2022. At the moment, there are more than 600 quantum technology companies globally. And all the big names, the big tech companies are actually investing a lot in quantum as well. So here you see Google, IBM, AWS. They are one of a few of the biggest players for quantum technologies. Like IBM has been investing in quantum computing for more than 30 years. And then Intel is recently getting in as well. NVIDIA on the software offering and integration part is focusing a lot more in quantum computing since 2025 as well. So, and then of course, there's a lot of big companies who are the users, and then a lot of startups. So maybe from this chart, you could also see a little bit more clearer how the commercial landscape is, right? So you can see IBM is really big because they invested really early and they have a lot of customers from their consulting service. And so those becomes natural customers for their quantum computers R&D as well. And then similar with Microsoft, right? So naturally they have huge market with them as well. And NVIDIA is growing as the user side, right? We can see there are lists of a very incomplete number of users. So JP Morgan, for example, in the banking sector, the finance sector, they or one of the earliest banks to invest in quantum computing, and they are still probably at the moment one of the largest investors of quantum computers in the financial sector. And then there's HSBC and Standard Chartered, which they also have their own quantum R&D team doing quantum things. But a lot of other companies like Boeing, Wells Fargo, ExxonMobil, or Samsung, they are collaborating a lot with quantum tech companies to see what are the potential impact that quantum computing or quantum technologies could bring to the future of the technology sector. Okay, and moving on. There's a lot of investment, right? Why are people interested in investing? Investing has to come back with returns. So this is a market size report by one of the McKinsey report. I would say there's a lot of such report, and every report gives very different numbers. So the McKinsey has a more moderate or like tuned down kind of estimations of the market size of quantum computer by 2040, and which we can see that everything adds up together could be about 200 billion US dollars by 2040, and it really depends on how well the technology is developing, right? So this is a very I would say, a safe estimation of the market size, but there could also be other applications of quantum computer that we cannot foresee now with our eyes, which happens to a lot of other technology sectors. So now we'll come to a little bit of physics, right? Before we're just talking about terms and the markets. Here is a little bit of physics. What is actually the thing that we use for quantum technology? Why is it so different from classical ones, right? So the first thing that you do for quantum technologies is to choose a physical system, right? Right now, classical computers just everybody use almost the same kind of devices, but for quantum computer, this is super non-trivial. This is an example of rubidium-85, a neutral atom that can be used for a qubit, like physical systems that we do quantum computer on. And we need to choose a two-level system that are stable and also accessible, right? We have to be able to do things with them, and then they also give us reliable results. And once we have a choice of the two levels, so for example here, if I point it out, is this state that could be your state 0, and then this state could be your state 1, right? And then once we choose these two states, we need to put them in an environment that is isolated from everything else, all the noise that we don't want, to make them like reliable. Because the nice thing about quantum is that they are so small, so precise, but then the drawback is that they are super sensitive. They are sensitive to a lot of things that would not be, we would not care in a classical world. So one really needs to shield them off from a lot of noise and other things to protect them from the environment. So this is something that we call a qubit, approximate two-level system, right? And then after we have those two-level systems, we need to do operations. Like we need to be able to flip 0 to 1. We need to be able to talk across different qubits, which we call like entangling gate, things like that, to do operations on them. And this applies for almost all the quantum technologies. But the difference is that for the physical systems, what we choose, it's still an ongoing, I would say, R&D topic, right? So this is some examples of the hardwares that people are investing on and doing research on. So this, for example, the one in the middle is superconducting qubits. They are the ones that Google and IBM are using at the moment, and for at the current stage, they are probably also the offers the best performance of quantum computer chips. But they do have competitors. For example, the trapped ion qubits, which is the architecture that IonQ and Continuum, which is the two big startup companies that I mentioned just now. They're using this system. And then this is a neutral atom system, which is like trapping single atoms at a desired location, and then we operate them as they are every one of them represent a qubit. Okay. And then we have photonic qubits, which use integrated photonic chips. And then there's spin qubits, which is very much similar to the semicon industry. And as well as something that is quite interesting, that is using diamond to carry qubits. So this is something we call diamond NV center. N is like having replace one carbon atom here by a nitrogen and then put a vacuum. And the difficulty of this, I'm just talking about this because this might be interesting, is diamond, right? We actually are implementing impurities inside the diamond. Not like the diamond industry, you want it as pure as possible, but we want the diamonds to be to have impurities, which then we can actually shine light into it and give us response because of the impurity. And the spin qubits and diamond NV centers are very popular sensors. However, the rest of this are very good candidates at the moment for quantum computer chips. Okay, and this is just to give you a look of what a quantum computer look like. So this is one of the most advanced quantum computers that one can buy in the market. It's from IBM, System 2. The thing in the middle, but I think this is just it's actually the real picture of this IBM System 2 in their headquarters, but also, of course, packed nicely for the photo. The things in the middle, right, is actually this thing that you might see sometimes on the newspaper, is what we call a dilution refrigerator. And inside here, I'm not so sure whether you can see it clearly on the screen, is the chip. So there's a tiny little chip inside this refrigerator, and they are connected by microwave signals to the outside of the world. So those are actually the implementation wires. And because it's superconducting qubits, they actually needs to be put in a very cold environment, like a millikelvin. That's why we need this big cylinder thing around it. The dilution refrigerator, actually, they are very expensive fridge. Each one of them could cost millions or if tens of millions for big ones. And they really needs to have very good cooling technologies because all the wires also get heated up. So we need to make sure that the superconducting qubits, the superconducting material are superconducting, right? They cannot be heated up too much. Okay. And next, right? So now we see the investment, we see the hardware effort that people are putting into. But why, right? Where does the power of quantum information come from? And the answer are these two big jargon words, right? Superposition and entanglement. I'm going to do the quantum qubit and classical bit comparison here to give you a brief understanding of what they actually means, right? So for a classical bit, we say that's usually 0 and 1 for the programming language. We can also say that they are like two faces of a coin, right? So the head is like 0 and the tail is like a 1. And then for quantum computer, we use qubits. The representation of them are just very simple. We put them in this thing that we call the cat. And then this becomes quantum state. So we have the representation of quantum state 0 and quantum state 1. However, the difference is that, right, we are not only having head or tail, 0 or 1, we can actually have a state that is in any continuous superposition of the two. So for example, this state carries a 0 absolute square probability that is in state 0, and then a 1 square probability that is in 1. Okay, so any state of this form could be a good quantum qubit state, which in a sense that a qubit can encode much more information than a single bit. Okay, and this is what we call a superposition. Okay, so a superimposing 0 and 1. And then let's see how does this superposition actually gives us, right? So when we have a state of a coin, a classical bit, we can say that this is a mixture. Maybe you flip the coin P, with probability P, you get head. With probability 1 minus P, you get tail. Very often for a fair coin, the P is just 1/2. Then we have half and half probabilities of getting head or tail. It's a fair bet. But then P can also be anything by like making an unfair coin or do something with a tossing that the magician can actually demonstrate for us, right? So there is actually a state of the classical coin as well. It's of this form. However, for the qubit, a superposition qubit state like this, the state of this qubit actually has two more terms, which we call quantum coherence. The first two terms are exactly the same as the classical, like a coin situation. So this is probability of getting 0, probability of getting 1. But then because of the superposition, it offers quantum coherence. Then we have two more terms that you would never have in a classical world, which is like it operates on the 0, it gives 1, it operates on the 1, it gives 0, which is the third term means. Okay, so this is what we call quantum coherence terms. And unfortunately, with noisy systems like what we just now said, that errors or noise from the environment, we could lose the quantumness of the state. Losing quantumness of the state really means actually losing quantum coherence. That these two terms will become very small, and then this state will become more and more like a classical qubit. That's what we certainly don't want for quantum computing. So superposition is something that only quantum system have, only qubit have, does not exist in classical bit. Just want to make it straight. And then if we look at the power of the superposition, right? Why are we saying that this is so powerful? If we have just one qubit, this is what we've seen before. And if we have two qubits, now we have 0, 0, 0, 1, 1, 0, and 1, 1. And all four states could give us a superposition state. So it's even like exponentially more terms than what we had in one qubit that can survive simultaneously on one, or be represented on two qubits. And then if we have 50 qubits, right, what does it look like? I cannot even write out the terms, because if we do a little bit of math, this gives us 2 to the power of 50 different combinations. So 2 to the power of 50 different terms that if we want to write it out. And that's really impossible to write it out in a very simple sense that 2 to the power 50 is larger than the number of atoms on Earth. So there's no way that we could actually represent it in the classical sense, right? So if a classical computer wants to write out this particular state of a 50 qubits, they just cannot do it because we don't have enough materials, resources to represent it. Okay, to store it, to represent it. And the limitation of classical computers are actually at the moment of 43 qubits. That's what the largest supercomputer that we have can reach. So 50 qubits is definitely far beyond the reachabilities of classical world. And then there's also entanglement. So entanglement does not exist in a single qubit because it actually involves multiple parties, right? If we have 2 qubits, this is the state that we saw just now, right? And so there are different options. What are the parameters? And for example, you could have a state like this, and then you could put out the 0 for the first qubit, and then you have the leftover for the second qubit. They are actually not entangled. They are separable. So this one does not offer us additional computational power from the because it's just not entangled, right? But if we have something like this, 0, 0 plus 1, 1, this is something sometimes, this is called a Bell state. And this cannot be represented in 2 separate entities, right? They are really one of the same entity, the 2. We can never separate them and do things like as if they are not connected. So this entanglement can exist in much higher dimensions, give us more powers of doing something locally, and then that has a global effect. Okay, that's the power of entanglement. Okay, I'm just going to put this part a bit shorter in the concern of times, right? The measurement, just not to give you like a wrong impression that, okay, we have 50 qubits, that it can represent so many things, that's so amazing that maybe we can use that for everything. That's not true, okay? So we have 50 qubits representing a lot of bit streams, but not all these informations are accessible by a single measurement, okay? Unfortunately, every time we do one measurement on 1 qubit, we can only get 1 bit of classical information. That's because we use classical detectors, right? We use a detector that gives us a signal. And the signal can only tell us, okay, this is a 0 or 1. One signal can never tell us what is the real A0 and A1. If we want to know the real state, what can we do? We need to repeat the experiment many, many times and then get a statistical understanding of what is A0 and A1. But even though with this, we can actually try to do it smartly. We try to implement or find quantum algorithms, quantum circuits, so that one of the particular bit stream result, it's very, very high, like 99.9%. So when we do one measurement and find out something, it actually gives us a lot more information about what we actually want, right? Which, for example, search algorithm, if we put the correct result probabilities being close to 1, then by a single measurement, we actually know what it is to a very good extent. We can never be 100% sure. That's the quantum world. Okay, and then for business, if you are not doing quantum computing, you are not building a quantum computer or all that, why shall we still be interested in quantum computing, right? What are the applications that potentially quantum computer can have an impact on? So those are a list of a few important ones. There's material science, healthcare, and high energy physics. So this is more for the research exploration, but material science and healthcare, they are of very important real world applications. For example, you can use quantum computer can help to design better batteries, catalysis, and or even superconductors, new materials, and then to do drug discovery, and also can help to understand biological data much more better than classical algorithms. And then so those are still in the sector that I would say, coming from a physics point of view, natural for quantum computers to handle, because materials or drugs, which are molecules, right? They are quantum systems, like by nature. So they use a quantum computer to do a quantum system simulation. There's a natural link, and then there's a natural reason why quantum computers can do better. But then we actually also have another category of things that quantum computer might be able to help and impact a lot, which is optimization and maybe AI as well. So, but those are things that we have a classical algorithms, we have a classical ways of doing optimization. But then quantum computers could actually help improving the algorithms, make it more, give us a better result, or shorten the decrease the resources that we actually need. Okay, so optimization is very important, or a lot of the financial industries are looking into. For example, risk analysis, portfolio optimization, and pricing of derivatives are the very popular use cases that people are looking into for financial related industry. And then the next, I'm going to talk very briefly about quantum plus AI. That's because it's very popular topic that people like to put quantum and AI together. But what is actually quantum plus AI, right? So there's two things. The first thing is quantum for AI. And this quantum for AI is very much at the research status. It's nothing that is ready to deploy at the moment, but there's a lot of excited research result coming out every now and then. So it could potentially have large impact, because here we're actually really using quantum machine learning models to improve artificial intelligence, right? So the model themselves are essentially operated on the quantum computer using quantum enhanced algorithms. Or I would not say quantum enhanced, but real quantum algorithms. And then there's a second tier, which at the moment is actually more important and being implemented already. That's AI for quantum. So for quantum computer, we need to analyze the noise. We need to optimize our circuit. We need to handle a lot of parameters like we just now showed. So, and to do this, we actually really need very good AI tools to help us giving the best parameters that we could put in a quantum computer, and also do very fast executions of quantum error correction. So AI for quantum is a must, we would say. We need good AI algorithms to make quantum computers, even large-scale quantum computers, even possible. Okay, so I'm going to do very fast here, talk about what is the state of art, just give you a few feeling on that, right? So if we compare the classical computer development timeline, from vacuum tube to something that is useful, the model that we have now is integrated circuits, right? That took about 50 years. And then from integrated circuits to the Pentium Pro is one of the systems that I got to know when I was very little. That took another 37 years. Okay. Now, when we come to quantum, the hardware from the very first proposal was an NMR system, very close to the NMR used for this medical imaging. And then from there to eventually, if we take the example of superconducting chips, that took about 20 years, okay? And now from the very first superconducting chips to what we say a useful quantum computer, that's also what we call the fault-tolerant quantum computer. How many years do we actually need? I would also like you to think about this, because this is the answer that I will get every time when I go to a panel session or give a talk. How many years? And I never have an answer for that, because there is really no answer, right? So if we look at what people, the roadmaps of companies and all that, it's maybe around BOC, so 5 to 15 years, we would say, depending on how they actually see, define what is a useful quantum computer. But with the roadmap, probably in about 10 years, we should have something that gives us real impact for the real world. However, that could also take longer if there's a technology bottleneck or something like that, right? Or it could take shorter if there's a breakthrough in the technology. So we actually never know. We can only say right now the estimation is somewhere here, but either left or right are certainly possible. Okay, and then a quantum computer is actually really a full stack development. We need hardware, we need middleware, we need algorithms, right? And because of this, there's actually a lot more around it that needs a whole industrial effort. Like we also need control electronics, we need good use cases, we need new algorithms that comes from things that we do not have right now. And so there would be a huge ecosystem covering the quantum sector. And just to touch on where we will go, right? This is the state of art right now. We have some powers that quantum computers show that it can do. And then algorithmically that there could be some quantum speed up. However, we are not at the point where we actually have useful quantum speed up demonstrated. But this could be improved by having better hardware, good quantum error correction code, and improvement on either quantum or classical devices, or improved by having new algorithms and new use case discovery, right? Then this intersection part would be much bigger, and then we will see when this useful applications of quantum computers come to us. I really believe that we will definitely see that one day in the next maybe 5 to 15 years. Okay, and the last thing that I want to just mention is something actually super important. It's something that NVIDIA and a few other companies are working on, the giant tech companies are working on right now, is to make the next generation supercomputer, okay? So the next generation of supercomputers is going to be, there's a part of quantum processor, there's a part of CPU, there's a part of GPU. We need to optimize the workflow to assign tasks that works the best on each of these components, and to do applications and to do things that we cannot imagine what the supercomputers can do today. And this would be the supercomputer future. There's no way that we can actually avoid that. So if you think that quantum computer is not concerned, I would say it will be, and a big component for the supercomputer future if we want really to advance the technologies that we have right now. Okay, I think I'm done. So thank you. If you have any questions, I think let me jump out and see the chat if we have any questions. Or I see quite a few
Yes, thank you.
questions.
It was a very insightful presentation. Let me share the chat on the screen so we can see the different questions.
Okay.
Whoa, see, there's a LinkedIn user as well as Fabio. There's a lot of technical questions. Just let us know whichever one you want to take up first.
Don't require most. What qubit type doesn't require almost okay temperature? Okay. Yeah, I can do this. So most of the ones that we're doing, I think somebody has the microphone on. There's an echo. Okay. So like things that really deals with a very tiny quantum systems like we mentioned superconducting. That's because we need superconducting materials. They naturally need low temperature. There is trapped ions and trapped atoms. They need to be very cold as well, although less cold than the superconducting chip, but they also needs to be in the range of macro Kelvin because of millikelvin. Because the atoms, if the temperature is higher, they will just jump around. They will not be located in the position you want them to be, so you cannot address them reliably. And but silicon qubit, so semiconductor type of qubits and this diamond in the centers, they don't require low temperature. So they are very good room temperature quantum devices. That's why they are used for quantum sensors. So you can bring them around. That gives you reliable outcomes. Yeah. And then do you need a different language to program a quantum computer? The programming language, fortunately, almost everybody still use Fortran. But we do have a lot of different packages and platforms that people use for to program a quantum computer. Because, for example, if you want to operate a gate, then or like let's say the Shor algorithm, you will not write actually a code like we do with classical coding, right? We will not write the code from scratch. You go to one of these online libraries, for example, Qiskit, which is developed by IBM, is very popular, one of the most popular ones. They have a lot of packages for doing such things like optimization and Shor algorithms and a lot of others. Google has its own program called Cirq. And then NVIDIA also has its own called CUDA-Q. So like every big companies would have their almost their own thing, but I would say they're very readable. And then there are softwares that can convert one to each other as well. Okay. Fortran. Fortran was actually popular for quantum simulation, but not for programming a quantum computer. Unfortunately, it's not the most popular one, but there are people who are using Fortran. Okay, let me. How would algorithms account for the fact that write down a qubit at its states? So I guess you mean that reading out a qubit would change its states. So we actually usually for most of these architectures we do the reading out at the very end. You operate them, and because once you read it out, then this qubit is like de-entangled from the rest of the qubits. Then you can it's not relevant for the system anymore. So you don't actually need to read it out when it's not necessary. We do the readout at the very end, so that a calculation already finished, and then you just need the result by one shot. Okay. Fabio, what quantum systems act as energy minimizer within a larger classical pipeline? Very good question. Okay, this is also one of the questions that I currently very much interested in finding out because there's no clear answer. If we look at the quantum computer producers, they will claim that quantum computer is energy saving, but cooling them requires a lot of energy as well, right? And then like the IBM System 2 that I showed you just now, it only contains about 100 plus qubits, and it needs a huge system. It's like really a huge rooms and about 4 meter tall probably, and the whole thing also needs a lot of control electronics. So it's not energy saving at the moment because we don't have useful applications that we can actually really compare with quantum with classical computers. But in the future, right, we want to optimize everything for whether by time or by energy. So if we have more tools in our toolbox, that could certainly be possible to minimize the energy. Like if something operates exponentially fast on a quantum computer, and that can certainly reduce the energy a lot if we do the right thing on a quantum computer, right? What do you think about Alibaba's recent pivot in quantum strategy? I think the Chinese tech companies are actually jumping in and out in the past decade. So Alibaba had a lab very long time ago, and then I think they kind of shrinked that department, and now they are going into it again. Which happened in quite a number of tech companies. I mean, the big environment changes, right? So now they have more investment, more time to actually do some core development. So definitely they also see this as one of the advancing thing. I think if we talk about Chinese companies, Huawei is also investing in it. And Japan is doing a lot from the government sector. There's Recon, and with their Fugaku computers, they are collaborating with almost everyone who has big quantum capacities to do quantum computing. Okay, maybe let me go up. I'm currently working as a Python backend developer, quantum and Qiskit and Verge's quantum algorithms and internships in this. Would you? Okay, so for this, you can actually, if you want a private chat, can find me on LinkedIn, and then maybe we can continue there. Not sure I appear as LinkedIn user. Yes, you do. Stefano, hi. Yeah, thanks. Thanks for liking the presentation. Fabio said bifurcation. I actually don't know what is bifurcation or pure quantum. But pure quantum, it's not a way to go. So none of us say pure quantum. That's why actually Japan has a large presence, because they open up Fugaku to all the quantum computers who wants to connect. Everybody needs a huge classical computer, or if not a supercomputer, to operate a large-scale quantum computer. Like Google has a lot of advantage because of their AI development, their algorithms, and also their supercomputer capacities, IBM as well. So putting quantum computer next to a supercomputer to optimization of the workflow is definitely needed. Not saying that even if I'm from quantum community, I would say the key is maybe optimization in resource and energy. Try to minimize the use of quantum computers. So don't use a quantum computer when classical computer can actually do the job, because it's going to be very expensive. At least in the next 10 to 20 years, quantum computer is going to be the chip is much more expensive than the CPU or GPU that you can actually get. Yeah, thanks. Toshiba, yeah. Toshiba is also doing a lot with Recon. Yeah, okay. So if you say purification by Ising model, so like annealing, I would say no. Coming from the real quantum computing world, we actually annealing, it's one of the earliest applications. It worked in some systems, but we actually don't see how this can actually give real implementations for some large systems that is useful, because it has a lot of its own limitations, right? Yeah. So quantum computer, like real quantum gates and circuits, is probably the way. And then for the annealing type, we would say analog quantum computer is also possible, but probably with atomic systems like neutral atoms. For example, using them to simulate a material, that could be also I would say even maybe one of the earliest applications that we could see that have a large impact. Yeah, I don't see any more questions, and we are also after 1 hour, so maybe I give it back to you.
Perfect. Yes, thank you very much, Han. There's so many interesting questions, a fascinating presentation. It's also good to hear some of your comments on quantum computing. It's a very exciting field, but it looks like we're still like a decade away from, us being able to use it, I guess, for, real applications. But I guess it definitely does have its place in the current world. I also had some questions I wanted to ask about, but a bit over time. So I guess we might be following up after the event and potentially organize another webinar. So thank you for the presentation, and thanks everyone for being here with us today. The stream will be available on YouTube. Since it's a YouTube live, it's going to be automatically uploaded on YouTube. You will also be receiving a link with our event recording if you have joined our community. Thank you very much. I hope to see you again soon. Have a great evening.